Good afternoon, friends, and welcome to the EduSat studio of IRS. Today lecture is on the remote sensing application to atmospheric studies. So, as you know that the meteorology is the study of science of various aspects of weather and climate, and also it is of the understanding of the physics and chemistry of the Earth as atmosphere and its interaction with describes the about the atmospheric composition, its properties, its motion in the atmospheric layers, and all this helps processes helps in the areas like the weather observation and forecasting, the modeling, and the monitoring aspects of many of the processes, including the air pollution. So, so this is the tri-junction, that is the interaction between the atmosphere, land, and ocean, which I talk about. So meteorology is all about the studying the processes of it, and this can be done through your instrumentations, your observations, and from your observations from the satellite also. Now, what are the important parameters to be studied? Now, there are various factors that determine the state and condition of the atmosphere. So, of these, the parameters include of these conditions can be sensed by certain parameters like temperature, air pressure, humidity, the cloud properties, winds, and many more. Of course, the radiation also includes in that, and the many particulates like aerosols and the greenhouse gases and all that. So atmosphere have different atmospheric layers, you know all about that, and these properties are determined by these some of the factors which I have mentioned, and this this helps in understanding the monitoring and also the forecasting aspect of, for example, weather forecasting. So one has to take into account many of the mathematical equations and the readiness or the study of these parameters in different layers, and these observations have to be put under some relative transfer equations, and then one has to model it. So this helps, for example, the forecasting of rain or the modeling of rainfall, or the prediction of the air quality, and so on. So most of your people know about all these. That is the constituents of the atmosphere. So no, not much detail about it. So you know that important aspect is that the atmosphere composed of constant gases, you know all about that: nitrogen, oxygen, argon, but also certain trace gases which are trace in number, and they are also highly varying, and this is induced by lot many anthropogenic and natural emissions, and the concentration is changing, hence we are concerned about it, which is the concentration of trace gases increasing, and then it causes lot many environmental and climatic effect. There are another component which are variable in nature, that is aerosol and water vapor. Aerosol is nothing about, it is a particulates that is larger size than they are the molecules or the gases, and this ranges from 0.001 to 100 micrometer. You have all heard about the particulate matter, aerosol particulate matter. So these are the particles whose diameter is 1 micron or 2.5 micron or 10 microns. So hence its name as PM1 or PM2.5 or PM10. So any of the gases or any of the components which fall under this size range is categorized as the particulate matter. So these are also highly variable in nature from one place to another place. The concentration changes, and also it moves from one place to another place as per the meteorology and other conditions. Water vapor is also another factor which is highly variable. So different latitudes you find different water vapor contents and is highly variable and is also changing the associated processes. When we talk about the Earth observation, so you know that there is a passive and the active. Passive, of course, takes into account the reflected radiation, senses reflected radiations, and active, of course, it has own source, so it it is reflected by, it is senses from the its own source. And in the passive sensor there are optical sensors, they can be microwave sensors. In the active sensors we have lidar and radar and so on. So different processes can be sensed through different sensors. So we'll discuss in detail in coming slides. Now what do you measure in remote sensing? So in remote sensing we essentially study how some of the properties of electromagnetic radiation changes when it interacts with the that is the bodies or the material bodies or the target material. So the important aspect how it changes is, one is the change in the intensity, the change in the polarization, or change in the angular distribution. So once it interacts with the body, that is electromagnetic radiation, so the intensity, polarization, or angular distribution changes, and which we sense at the sensor level, whether it is a satellite, and then we try to indirectly infer the properties of it. And when it passes through the atmosphere, so obviously there is a scattering or absorption from the atmosphere, and all three parameters, out of any three parameters we measure and we try to infer the properties, the concentration, and the important aspects of the atmospheric particles. So of course this depends on the characteristic of the material, that is whether it, what is the size of it, what is the what is the refractive index, and so on, and also the interaction of the electromagnetic radiation wavelength or the frequency. So that is this is the, when the propagation happens electromagnetic radiation in medium, so two things can happen. One is the that is a scattering, and another is your scattering and scattering and absorption. So scattering happens, you know that you all know there are different kinds of scattering. Rayleigh scattering is one of them, when the particle size is very small as compared to your wavelength. So so when a electromagnetic radiation passes through the atmosphere, so and then after reflection it reaches the satellite. So in that whole atmospheric layer, so the particles can scatter while molecules can absorb, a small molecule can absorb. So what happens is, and that is the absorption occurs when the molecule has the same frequency as of the incident energy. So it is a resonant frequency. So whenever there is a resonant frequency, the absorption will happen. So thus the scattering and from the scattering and absorption, the properties of the atmosphere, as I said, the properties can be the concentration, the number density, the other types of properties, and there are many optical and other thermal properties also can be assessed from the interaction of it. When we talk about the absorption, so the radiation interacts in the with the atmospheric gases in the following way, that is the ionization. So what happens is, the short wave or the ultraviolet, there is strong energy. So in the ultraviolet and visible region, energy is very high. So this helps the electron is now shifted and is stripped from the atom, and then molecule is torn apart, and such type of dissociation known as ionization dissociation. Similarly, the infrared radiation helps to for vibrational transition, and far infrared and microwave for the rotational transition. So you see that here the uh, different atmospheric gases are written. So, ozone, water vapor, oxygen, methane. So all these have absorption in the specific wavelengths, because the electromagnetic radiations they interact with the atmosphere in certain frequency or certain wavelength. So this is in the infrared, so like CO2, methane, so it interacts with the atmosphere or with these species in the infrared wavelength. So there is a absorption in this wavelength only. So there is a specific to this. So we know that, and then when we design a sensor at the satellite level, we design in this wavelength. The sensor will be in the infrared wavelength, and when it senses the radiation coming from the atmosphere, so we can infer the properties of these species. So there can be different sensor in the same satellite. It can be optical sensor, it can be UV sensor, it can be infrared sensor, it can be microwave sensor, and we can directly or indirectly measure the concentration of different atmospheric gases. So in a clear mode, these slides can depict, for example, water vapor. So the absorption is in that is the optical and infrared, that is near infrared. So 0.9, 1.1, 1.4. So these are the absorption of for these H2O. So any sensor which has to be designed to measure the water vapor has to have a wavelength of these ranges. Oxygen, so it is 60. There can be why 2-3 bands are required, because somewhere can be weak absorption, somewhere can be high strong absorption. So it is not that it will absorb only in microwave, but there will be weaker absorption in optical region also. So you find different wavelengths written, because there can be strong or there can be 2 or 3 peaks for absorption. One can be slightly low absorption, so it can be high absorption, strong absorption. So carbon monoxide, methane, carbon dioxide, so all these are having in a infrared domain. Nitrous oxide, tropospheric ozone, NO2, sulfur dioxide, SO2. So all these have a specific absorption lines in the atmosphere, absorption bands in the atmosphere. Now what happens here is that so what happens is in the satellite satellite things, we the satellite detects scattered solar or emitted terrestrial radiation. So we have discussed with this, and we know that distinct absorption spectra of each trace gases, as we have seen. So each depicted, we put a sensor, and then this is designed to measure those specific species in the atmosphere. So we can say that we can identify a spectral fingerprint for each atmospheric constituent. Now what happens is all satellite remote sensing sensors are based on use of the electromagnetic radiation that we know, and it interacts with the atmosphere as many constituents. So most of the techniques today apply the passive remote sensing. So most of the sensors are passive remote sensing, where the that it doesn't have a specific source. So sun is the main source of sunlight or source of light for the illumination. So now, as we have seen in earlier, the specific species in the atmosphere, they are identified using the spatial that is spectral dependence of the absorption or emission signals. Now in the UV domain, that is ultraviolet, which I discussed, that is the ionization ionized dissociation. So in the UV, the thermal emission is minimum, so there will be no thermal emissions. So the light needs to be considered only, so sunlight, so it is reflected. So in this, the as Rayleigh scattering depends on the wavelength, we know that Rayleigh scattering is inversely proportional to the fourth power of the wavelength, that is lambda raised to power -4. So a large importance is given to the UV. So UV is smaller that is smaller in wave size. So smaller particle will have a Rayleigh scattering in the UV. So many photons are scattered by this scattering property, and therefore the sensitivity is from the lower troposphere. So meaning that this has a strong wavelength energy, it can penetrate, and the particles here in the lower troposphere also can scatter, and this scattering goes to the sensor level, and hence we can identify or we can estimate the properties of the species present in the lower troposphere. For example, there are many sensors like TOMS, that is ozone monitoring, ozone monitoring sensor. It has ultraviolet and visible sensor. So which senses the ozone, not only the stratospheric ozone but also the tropospheric ozone, which is lying near to the surface. There is another sensor known as GOMS, that is the ozone, as another ozone monitoring instrument, which is also designed under same wavelength. Now what happens is in the near infrared, so in the near infrared, the scattering is not of much relevance, and main here is, and also the thermal emission is also weak. So the both these are weak in nature. As a result, so what are the photons which the sensor measure is it interacts homogeneously. So the scattering is homogeneously in this column, meaning that it is good for your that is the total columnar. When you say the total columnar scattering, it is uniform for that, and it senses the species in the total column. When we talk about the far infrared or infrared, so here the scattering is neglected. There is no scattering. Of course, there is a emission. So this emission can happen from, there are various layers in the atmosphere. So different layers will have different emissions. So depending on the temperature, depending on the water vapor, they will emit differently. So all the radiation or the emission which are sensing at the satellite level will have all the components coming from different layers. So depending on the mathematical formula and the ranges and the vertical resolution, we can say that from which layer the species different composition we can calculate. That is the profiling of it. Now talking about the satellites. So as you know, the satellites are classified differently. That is the geostationary satellites or the polar orbiting satellites. So in this platform, there are some meteorological satellites which are dedicated only for studying the meteorological processes. So for the under the geostationary platform, we have this one high resolution, high temporal resolution. These are GOES, Meteosat. These are countries. US has a different series of GOES, Europe Meteosat, Japanese GMS, and India INSAT. So different series of INSAT satellites are launched, like INSAT 2E, INSAT 3D, INSAT 3DR. So these are for meteorological purposes, and these are number of parameters can be measured. So like outgoing long wave radiation, precipitation, sea surface temperature, upper tropospheric humidity, snow cover, fire, smoke, aerosol. So these are the different atmospheric components or species or the processes which can be measured through these satellites. Similarly, we have a polar orbiting satellites which has a global coverage, like we have ozone, GOMS, MODIS, MISR, OMI. So these sensors, these MISR, OMI or aura, not only measures one parameter but a series of parameters. For example, it can measure the aerosol, it can measure the ozone, it can measure CO. Some sensor can have a CH4 depending on the wavelength of the sensor and purpose for which it is launched. So a sensor cannot measure all parameters, but a sensor can measure one or more parameters. So these are the name of the sensors: Aura, VIIRS, Nova 20, and Xiaomi NPP, OceanSat, Tropomi, OCO, that is the orbiting carbon observatory, and these can measure these different trace gases, aerosols, on the radiation budget, fire, that is fire occurrences, smoke, and so on. Also, these measure the total column measurements. But when I said when the previous slide also said that different layers, the concentration can be different. So for the profiling of the atmosphere, different what are the different concentration at different heights of the atmosphere or different layers. So we have to measure through sounders. The sounders are the technique from which it can have a profiling of the atmosphere. So these are some of the satellites, these sensors in the different electromagnetic domain. It can be in the microwave domain, it can be in the visible domain, it can be in the infrared domain. So these are the abbreviations of some of the sounders. So inside 3D also there is a sounder. In GOES also there is a sounder. AIRS also there is a hyperspectral sounder. So in the inside 3D we have 19 channel sounder. In AIRS we have more than 2000 channels, 2000, and ERC we have around 8000 plus channels, measurement of high vertical resolution profiling. So these are optical, hyperspectral, or microwave sounder for different purposes. So as I said, these are the regional coverages of the meteorological satellite. So they have a regional coverage. So this depicts the regions of, like for example, India. So it has this much region. Meteosat, GMS Japan, GOES, and GOES you have two, because Eastern Pacific and Western Pacific. So two tandem GOES satellites, meteorological satellite. So these are the glimpses of it. The carbon monoxide total column, as a polar orbiting satellite, total column, ozone, HCOH, CS3OH, ammonia, ozone, and so on, SO2, nitric acid. So these are the some of the species which can be measured from these satellites. So this is total column polar orbit or meteorological satellites also. Now this is now the real-time measurements, and this ERC is a hyperspectral sounder. This measures in different domains, and this is what we call as hyperspectral sounder, and this is the capability to track the gaseous plumes that is related in the atmosphere after the extreme events. So suppose there is a volcano or any other event, so it can the different gases or different species what is emitted, whether there is an accident fire, there is a forest fire, there is a stubble fire, industrial emissions, volcanic activity, or any other thing, it can measure or monitor the different types of species. Number one. Number two, also it can also see how this species, or how this pollution, or how the gases are distributed from one place to another place, how it travels from one place to another place. So through the modeling also we can see, and through which incorporates not only the meteorology but also various aspects of meteorological properties, including the what you call the different interactions in the different layers, the species composition, the number density, all this goes in the modeling, and then we can predict what is the track of the pollution from one place to another place. So these hyperspectral observations have improved the medium range forecasting or weather forecasting system, and it provides a very important role or the important input in the climate monitoring aspects. And currently this ERC or AIRS is a hyperspectral which gives a lot many species information, and also the GIFTS, So this is a geosynchronous imaging Fourier transform sounder. So this also helps. Is around 18 and 1800 channels, and it is a very high resolution sounder, which from the geostationary platform. And the importance of geostationary platform is every 30 minutes we have the data, as compared to the polar orbit where we have only 12 hours or 24 hours of data. So this helps in monitoring of the high frequency domain. So every 30 minutes, so in a day we can have around 12 to 20 data sets, and this helps to track very at the very fine resolution, time resolution. So in a nutshell, this is the list of the different satellite sensors for different aspects of it. I have clubbed it energy, that is the radiation, greenhouse gases and aerosol, which are a part of the atmosphere. So you can see that the TOMS or GOMS or ASTER, so we have different parameters. OMI, MOPIT, so MODIS. So MODIS not only the aerosol but also different gases. CERES, MISR, tropomy. So these measure not only the ozone but CO, NO2, SO2, CS4. As I said, it depends on the wavelength of the sensor. So as I said, inside 3D, we not only we have imager, 6-channel imager, but also 19-channel sounder for profiling of it. And this is measurement for our different gases, or different not only gases but for example the land and ocean also. There are different products depending on the physics of it, and depending on the mathematical equations. From the radiation reflected and emitted, we come out with a different products or different information on the species. So it can be OLR, outgoing long wave radiation. So because it is a balance affected by the cloud and dust. So how much energy is coming, how much is being absorbed, and how much it is reflected back. So it is a balance of it. Of course, the rainfall, the UTH, that is the upper tropospheric humidity. So it is a significant impact on the Earth radiation budget. So as it increases, so what is the changes in the upper tropospheric layers? Of course, rainfall you find different resolutions, different time resolutions, and different spatial resolutions also. So basically, as rainfall can be measured from the ground, but continuous or the high temporal resolution we can have measurement from the satellite. So in that, visible as well as the infrared and thermal infrared can be used to have a high accuracy. So infuse these clubbing of the radiation from different wavelengths can help to find out the accuracy, more accuracy. So we have different methods of rainfall. So you find GPI, IMSRA, then aerosol also, aerosol optical depth. So this gives the aerosol loading, what is the concentration of aerosol in the atmosphere. Then these are the different products. You can see that now this is the vertical profile, that is profiling sounders. So mean surface pressure, elevation, then temperature profiles, water vapor profiles. So these are the important aspects: temperature and water vapor. Of course, ozone. Then different temperature, what is the skin temperature. Then also we can have a forecasting of it. From this we can have forecasting of all these aspects also. So this is the cloud motion wind. So from the wind also we can or from the cloud movement, from the different cloud every 15 minutes or every half an hour we have a cloud movement, and we can because cloud moves due to the wind, and from this we can generate the wind vectors. So you find that in the most of the images you find such of the things image where you find some of the vectors of and shows the direction and intensity both, and these are the clouds. So from this, at each that is the atmospheric layer. So it depends on the pressure level of layers depending on the height from the surface. We can see the winds, what are the movements of the winds, what are the strength of the winds. This we can easily see. This is the precipitation, gridded precipitation. So like this it will be every 3 hours accumulation rainfall. So every 3 hours how much rainfall is being captured by the satellites. So this is the one of the pictorial represent the map over this region, how it looks in the full disk form. For example, rainfall. So daily rainfall you can have, every 30 minutes rainfall, every 3 hours rainfall. So whatever the requirement is, one can have, and this product is easily freely available, and one can download the data and use as per one's requirement. Now how do we interpretation of this? For example, you see this is an inside map or picture where you see some dark, bright, and some visual aspects. So object with high reflectivity, that is high albedo, that is, it means it is the solar energy is being reflected, more reflection is happening over the surface, that's why we have bright. So these are all bright, you know that this is cloud and deserts, so they reflect, that is high albedo, that is reflect the solar energy, more solar energy, and hence we see more of the brightness over cloud or deserts. So then objects with the lower albedo appears dark on the satellite image. Example, water. So water we have a so absorption is more, refraction is less, so it appears dark. Now reflection intensity differ depending on the cloud thickness also. Different cloud heights, different cloud thickness also we have reflectivity also differently. So we can also have a visual interpretation that this cloud is different from this cloud, and also the texture is also different. So we can say snow we don't have here, snow reflectivity is not high, so here cloud, because the cloud reflectivity will be more and the texture is also different. So land, cloud and ocean are easily discernible, means you can see the land, ocean, there is water and your cloud. So we can see the higher cloud as well as the lower cloud. Height of course we cannot judge, but we can see this is lower cloud and this is higher cloud. And but only limitation is this can we only see through the only daytime, because it depends on the reflection. So you can see that easily see, and from every 15 minutes or half an hour we can see the movement of the clouds. So hence we have, I told you that we can make the wind vectors from these cloud movements. Now the infrared. Now in the infrared imagery, this is emission. Okay, this is not reflection, this is emission. So it can happen day as well as night. So emission can happen both ways throughout 24 hours. So infrared satellite measures radiation output from Earth into space, and in this spectral band atmosphere is relatively transparent to radiation upwelling. So emission is happening. Again the clouds, land and water are easily discernible. So we can see clouds, land and ocean is clearly. Now the what happens is, now here one has to remember that the clouds have low temperature, so emission will be low, so it should be dark. Clear? The emission from the temperature of the cloud is low, less temperature, and emission will be low, so the temperature will also be low. So this is it. So what we have done is we have inverted it. It means, what I say is, these clouds will have low temperature and low reflection. So when there is a low temperature, so this will be dark and brighter, and land will have a more temperature, so it will be bright. But actually our eyes are had the habit to see clouds at white, so we have inverted this image. Here the actual reflection is from the more reflection is from the cloud, so hence it is white. But here the reflection from the cloud is less, so it will be dark, and land will be bright. But due to our uniformity in seeing the clouds as white and habit of seeing the white, so we have inverted it. So opposite. So low temperature we have made high temperature, that is white color, and high temperature we have made low, that is black. So here we see this is low temperature, but this is white. So this is cloud. Now here we can see the coastline is also separable. The land and ocean is separable. The clouds is separable. So in the infrared, in this imagery uh, helps to uh, helps to see the pattern of the the clouds, different types of clouds, but the texture of the clouds it cannot be ascertained. So what we can see from the optical imagery, the texture, this only it hinders to know about the texture. Rest easily identifiable. The low clouds, high clouds, the temperature of the clouds can be easily identifiable. Now third imagery is the water vapor. So water vapor is around 3 to, that is 6.7, that is 5 to 7 micrometer. So what happens is this is absorption channel in 6.7 micron. So it detects the moisture content in the middle and upper troposphere, and clouds appear dark. Similarly, same thing. So the cloud having more water vapor will have low temperature. So it means the reflection, the emission will be low. So it will be dark. But we have, for our easily interpretation, we have inverted the image, similar like infrared imagery. So here also we have done similarly. So for this region, these both images are inverted, and these images are densely sliced and classified according to the cloud top temperature. So different cloud top temperature values we have and sliced it, different segments we have made it, and we can easily notable what are the different clouds, whether it is cirrus cloud, whether it is stratus cloud, or what type of cloud we can identify. So regions of high moisture absorb radiation from below and therefore correspond to lower brightness temperature. And from the bottom temperature or from the cloud top temperature, we can identify different types of clouds. So in the nutshell, this is the thing in the visible, infrared, and in the water vapor, how it looks and how do we interpret it. Now, of course, this is also used because these type of satellites and this type of process, water vapor or the temperature, this is used for the identification of or monitoring the tropical cyclones. So infrared images show the temperature of the cloud tops, and they also show the deep organized convection characteristics of the tropical cyclone. So satellite images not only show the storm location but also used to estimate the intensity of it. So how much, depending on the wind and the wind speeds and all that, and the water vapor content, and the of course the cloud and other aspects, other properties, we can estimate the what is the rainfall of it, what is the rain intensity, and what is the wind intensity. So this tries to satellite images helps to quickly identify and establish the facts and figures on the intensity and the pattern of the formation of the cloud and the cyclone. In the visible observations, it shows the reflectivity, and because of this, that is the cloud high albedo, we can see the visually what is the cloud formation and what is how variable the clouds are. So all this club, the infrared, the visible, and water vapor, this helps and being high resolution, because as you know that the cyclones, they change the trajectory very fast. So the geostationary platforms, the satellites helps to identify and track the cyclone activity in a high frequency manner. Every 15 minutes, every half an hour, every 3 hours, we can have the location and the trajectory of the cyclone. Of course, this can also be used for the fog intensity and the formation of the fog. And this fog is because fog are the lower stratus clouds, and this possesses very serious concern because due to in the winter and the high pollution episodic events, fog is easily formed, and this have a lot many problems in the road transportation, air and shipping traffic, and hence there are a number of observations with which the fog formation is also forecasted and broadcasted, not only from the ground observation but also from the satellite observations. So in the weather report also the fog information is given for a specific months during where we are concerned about the fog and all that. So there can be a low density of the fog or high density of the fog, and how much area special area it covers. So the fog can form in the daytime as well as night time. So the observation or the monitoring aspect of it is entirely different. The algorithm for daytime fog or nighttime fog is entirely different, because in daytime we have visible channels, and in night we do have infrared. So those aspects also has to be taken into account, and the algorithm is entirely different. Of course, the pollution aspect I just discussed, though pollution is like trace gases or the atmospheric aerosols. This not only possesses the health, the air quality, but also affects the environmental concern, and the atmospheric chemistry also. And these are the main culprits, you know very well know. So these the satellite platforms, for example, the geostationary satellite also helps to this is geostationary inside 3D. So every half an hour, every 15 minutes, every 2 hours, so as per the requirement we can see what is the pollution aspect of it. For example, like nowadays there is high polluted regions in the northern India. So one can monitor in a very high resolution scale, at a high temporal resolution scale, what is the concentration or what is the quality of the air from the satellite. So either in terms of the gases or in terms of the particulate pollution, one can estimate it. So what are the number of fires and the sources, and how this fire is contributing, or the relation of these fires emission to the pollution loading, and how this is transporting from one place to another place depending on the meteorology. So if we incorporate meteorology on it, so we can see the emission which is happening from one place, it how it, for example, Punjab and Haryana, it goes slowly according to the meteorology and other conditions, the boundary layer conditions, it travels to downward regions of the Indo-Gangetic plain. So this can also be studied. So aerosol optical depth over this region, then PM 2.5 and PM 10. So particulate pollution, different fine particles or larger particles, how they are distributed spatially, and which area they are polluting, that also can be monitored and measured quite well. So this is the condition of the stubble fires which happens, and how it propagates to the Indo-Gangetic plain and NCR region during the episodic events of the stubble fires. Yeah. So thank you so much.